Hello and welcome to another Advent of Code problem. This one is a graph problem. So I'm going to show you how I usually represent graphs in code and then show you how we're going to solve this. All right, so our inputs today, and we actually there are 3 sample inputs in the problem, but we're only going to look at 2 of them just because the third one is kind of long and I think these 2 are good enough. The inputs are the edges of a bidirectional graph. So wherever you see a dash, that means you could go either direction. So this means you could travel from start to A or A to start. Well, A to start's actually invalid, and we'll see that later. But I guess if you saw this, you could go from capital A to C or little c to capital A. And for part 1, we can visit a lowercase only once. So if we ever reach lowercase c, we can never go back to lowercase c on that particular path. But you can revisit uppercase paths as much as you need to. And the question asks us to compute all of the paths that go from start, this node here, to end, this node here. So let's just start. I'm going to make a separate function for this just because we have to call it twice. We'll call it compute. We'll take in a string and we'll return an integer for the number of paths that we're doing. And the way that I like to represent graphs involves a dictionary that maps the node to all of the nodes it can go to. So I'm basically keeping track of just the edges. And for this, I'm going to use a default dict with a set in the middle of it. So the key is going to be the start and the set is going to be all of the destinations that are possible. For line in s.splitline, so we're just going to do the parsing now. Source dest equals line dot split on the dash. And since these are bidirectional, this means that we're going to insert we're going to insert dest into source and we're going to insert source into dest. Do that really quick. Edges source dot append dest and edges dest dot append source. That's really all we need to do to represent our graph here. Once we have that, it's just a traversal problem. We can either do depth first or breadth first. When I solved this live, I did it breadth first, so I might as well do it depth first here. Why not? And we're going to use basically the same pattern that I used when doing a depth first search on the basin problem, where I have a list of paths. Of course, in that one, it wasn't paths, it was current positions, and we were able to store state elsewhere, but we're going to store our state directly in our path here. And we're going to start at start, and we're basically just going to use this same pattern. Again, not using recursion, just because I find this a little bit easier to understand what's going on. Basically, we're going to keep track of what we need to do in here, loop while there's still things remaining, and pop off each path and process it one at a time. Okay, so once we have a path, we want to be able to consider all of the next places it can go. And fortunately, we have a mapping of edges here, so it's really easy to look that up. For candidate in edges path -1. So this is going to get the last element of our path, and we're going to figure out where we can go from there. And our conditions for part 1 is we can go to any path if it is uppercased, or we have not visited it in our current path. So if candidate is, if not lower, or the candidate is not in our path, that means we can continue this path onwards. So we can do to-do.append and just splat our path in here as well. So this is special syntax for splatting the current path and appending this tuple. I could also have written it as path plus and cant. That also works as well. But I kind of like the star syntax, so that's why I'm going to use it. Okay, so that covers kind of our iteration case. We also need to consider the end case, and we also need to count the paths at the end. All paths equals a set. And we know a path has completed if the last element of the path is end, because that is our destination. So if path -1 is equal to end, I believe that means that we're done. All paths.add path. And we can just continue because we know once we reach the end, there's no point in doing further iteration there. So this is kind of our termination case. And so after that, we can just return the length of all paths. and that should get us our solution for part 1. Let's try that out. Print part 1, input 1. So compute input 1. And if we do this twice, 2, let's see what that gets us. Assuming I don't have typos. Of course I have typos. Set.append. Yes, this is not append, this is add. I always mix up those. And 10 and 19, that is what we expect for part 1. Cool, so that's part 1. Just to recap, I used a map to sets to represent edges, and then depth first search here. And to switch this from depth first to breadth first, you could change this from a list to a queue, or collections.deck, and then instead of doing pop, you would do pop left. That way you always put things onto the end and pop things from the beginning. So you get your queue, your depth first there. All right, let's do part 2. Part 2 says we can only visit a lowercase, we can only visit one lowercase item twice. And actually, when I was solving this, this threw me off. I thought it was just that you could visit any lowercase twice, meaning you'd have 2 dupes per path, but you can only dupe a cave once. And again, you can still revisit any uppercase, and because start is lowercase, there's a new stipulation here that you cannot revisit start. So if you ever see start while continuing, you have to ignore it. And it still asks, what are all of the paths from start to end? Oh, I forgot to do the sample data. Let me get that real quickly. ESC 2021 day 12, part 2. I'm not going to look at the solution there. And 36 and 103. 36, 103. Okay, cool. All right, so I'm just going to adjust this solution directly. And so we're going to break the part 1 code, but that's fine. I solved mine separately. Okay, so we can still revisit any uppercase. We need to keep track of whether we have visited a lowercase twice or not. And what we could do is just like make a function that recomputes this over and over down here. I didn't really like that when I solved mine, so I kept a separate piece of state inside of this stack here that represented whether I had doubled up a cave or not yet. So I could just quickly check this value and in theory save myself some time. Double cave. So we're going to initialize that to false. We have not visited a double cave yet. And we are going to adjust our continuation down here. We actually don't have to change this at all. And we don't want, let's do this first. We cannot revisit start. If candidate equals start, we will just continue. I'm not going to bother revisiting it. If it's uppercased, we can. If elif candidate is upper, then we know we can just continue. All paths, or not all paths, to do dot append, and we have a tuple that's star path and candidate, and we also have our boolean. We don't actually modify it here because we're just uppercase, double cave. I think that's the right number of parentheses. Yep. A little bit tricky when dealing with tuple of tuples here, so be careful with the parens there. We cannot revisit start, so we've done both of these. We just need to handle this. So we can just say if the candidate is not in the path, we already know this is the first visit. If can's not in path, then we can also just do, I guess we can just do or can's not in path. These are the same case. We don't actually modify this at all. Otherwise, if we have not seen a double cave, if not double cave and path.count canned is equal to 1. So in this case, we have not seen our double cave yet, but we have seen exactly one of the candidate already. Then we can do and star path canned and true. So basically only allowing us to duplicate an item if we have not already duplicated an item. And once we have done that, I think that's part 2. Let's run that. We should get 36 and 103, and we do. Cool. So there's a little bit of fiddly logic here. It did actually take me quite a bit of time to come up with this idea, but I think it's fairly easy to understand. I kind of don't like having a Boolean just floating there without a name, so I might change this tuple element to be a named tuple. That would make this a little bit easier to understand what's going on. Just because this would have a name rather than just kind of floating. Of course, we give it a name down here, so it's not the worst. But yeah, and again, an alternative is just recomputing whether you've double caved in here. One approach to that might be using a counter to see if you have anything that's, anything that's doubled already. But this works. Anyway, hopefully you find this useful, and I'll see you around for the next day.